Hello. Today we'll look at the houses on the street puzzle. A man was reminiscing about a place called Louvain, which the Germans burned down in World War One. He used to visit a Belgian friend there whose house was on one side of a long street. The houses were numbered 1, 2, 3, and so on, without any gaps. The numbers on one side of him added up exactly to the same number as the numbers on the other side of him. He knew there were more than 50 houses on that side of the street, but not as many as 500. This puzzle was first published by Henry Dudeney in a December 1914 issue of the Strand Magazine, a local London publication. I shall present three methods of solving the puzzle. The first is from a paper by Behera and Panda, published in 1998, and gives a formula for all solutions. The second is based on Pell numbers, known since ancient times. The Indian mathematician Srinivasa Ramanujan was presented the puzzle by a student, Prasanta Mahalanobis, who has earlier solved it in a few minutes by trial and error. Ramanujan remarked that he knew not only how to find the particular solution, but how to find all solutions using a continued fraction. This is the third method. What is the number of that house? A school student at a higher level would have sufficient knowledge of sequences and algebra to answer the question. The solution. Let x be the number of the particular house and y be the total number of houses on that side of the street. If there was no restriction on y, we can easily get the following solution after a few trials. X equals to 6, y equals to 8. We see that the numbers on the left side of house number 6 add up to 15. The houses on the right side add up to 15. And so these sums are the same. But in this problem, we have the constraint y has to be between 50 and 500. We use the sum of consecutive numbers formula. 1 plus 2 up to n is equal to n times n plus 1 over 2. Sum of numbers less than x, 1 plus 2 up to x minus 1, is, according to the formula, x minus 1 times x over 2. Sum of numbers greater than x, x plus 1 plus x plus 2, and so on up to y, can be obtained by taking the sum of the first y numbers minus the sum of the first x numbers. So using the formula twice, we get this. So therefore, you have this equation. Multiply by 2, we get this. And then simplifying the equation, we finally get this. 2x squared equals to y squared plus y. We call x a balancing number if the sum of numbers less than x is equal to the sum of numbers greater than x. So the x we found is such a number, and we saw that we have the equation 2x squared equals to y squared plus y. Let us write y as x plus r. Then the equation can be rewritten as 2x squared equals to x plus r times x plus r plus 1 and that's equal to x squared plus 2xr plus r squared plus x plus r. So you get this quadratic equation, and the solution is r equals to this number. Now, r has to be a whole number. That can happen only if root of x 8x squared plus 1 is a whole number, and that means 8x squared plus 1 is a perfect square. Thus, x is a balancing number if and only if 8x squared plus 1 is a perfect square. If it's a perfect square, then this r will be a whole number because this is an odd number, whereas this is also an odd number because the square is odd. So you have an odd number minus another odd number that gives you an even number in the numerator. So divide by 2, you get a whole number. We shall find a generating function for balancing numbers. Let fx be 3x plus square root of 8x squared plus 1. If x is a balancing number, so is fx. That's what the theorem says, and we shall prove it. 8 times fx squared plus 1 is this. If you square it, you'll find you have this. Simplifying it, you get this or this. This can be written in this form and shows that this is the square of 8x plus 3 root 8x squared plus 1. So therefore, this is a perfect square. Therefore, fx is a balancing number. So that proves the theorem. We now show that fx is the next balancing number after x. Theorem. If x is any balancing number, then there is no balancing number z such that z is between x and fx. The proof. The function fx is a strictly increasing function. That's because the derivative f prime x, which is this, is always greater than 0. So this is a positive slope. So that's why f is increasing. And therefore, f is 1 to 1. And therefore, the inverse exists, f inverse x. And it's also strictly increasing, like this, with f inverse x less than x. Okay, you can see from this diagram. It comes from the fact that this function f x is always greater than x. So you have the result f inverse x is always less than x because it's a reflection of the graph of f in the 45-degree line. can use the usual methods of finding the inverse function to get the inverse function f inverse x. Using the usual method, it's easy to show that the inverse function f inverse x is 3x minus root of 8x squared plus 1. Now we compute this 8 times f inverse x squared plus 1. And we get all this. This is similar to the computation of 8 times fx squared plus 1, which we did earlier. And we see that it's a perfect square because it is this square. So this is a perfect square. And according to what we said before, since it's a perfect square, f inverse x is also a balancing number. We shall now show that there's no balancing number in between. We know that at the outset, 6 is a balancing number. 1 is the balancing number before it because 8 times 1 squared plus 1 is 9. So it is of that form. And this is a perfect square. Let x not equal to 1 and define the following number xn to be f of xn minus 1 for n equals to 1, 2, and so on. Thus, x1 is 6. This is a balancing number following 1. Let Hn be the hypothesis that there is no balancing number between xn minus 1 and xn. Clearly, H1 is true because H1 is saying that there's no balancing number between x0 and x1. And we know that there's no balancing number between 1 and 6. Assume that Hk is true. We shall prove it follows that Hk plus 1 is also true. That is, there's no balancing number z such that z is between xk and xk plus 1. Suppose, on the contrary, that hk plus 1 is false. In other words, such a z exists. That satisfies this. Then f inverse z is a balancing number, as we proved earlier, and since f inverse is strictly increasing, f inverse z must be between this and this. That is to say, xk minus 1, which is this, is less than f inverse z is less than xk, which is this. But this contradicts the assumption that hk is true because hk says that there is no balancing number between these two. Therefore, our assumption here that hk plus 1 is false is not true. That means hk plus 1 is true. So this concludes the proof by induction. Therefore, by the principle of induction, Hn is true for all positive integers n. So now we have a generating function for the balancing number xn is given by this formula, and we can use it to generate the y's. So x n, you substitute this position numbers, you will get x equal to 1, and then 6, 35, and so on. And correspondingly, y is equal to 1, 8, 49, 288, and so on. So we have the requirement that there are more than 50 houses, but less than 500 houses on the street. So this is the only solution that fulfills this constraint. So this is the solution. X is 204, Y is 288. That means the number of that house is 204, and there's a total of 288 houses on the street. Method 2. The quadratic can be rewritten to keep y in one place. So we have this. This is a completing the square method. We first multiply by 4 so that we don't have to deal with fractions. So we get this, and this is completing the square, you get this. So we have y in one place. Simplifying this by renaming the variables, x equals 2x and capital Y equals to 2y plus 1, we have 2 capital X squared equals to capital Y squared minus 1, or this y squared minus 2x squared equals to 1. This is known as Pell's equation, and the solutions have been known more than 1,000 years ago. The Pell numbers are defined by this. This is the definition of this Pell function. The solutions are then x equals to Pn and y equals to Pn minus 1 plus Pn. The Pell numbers can also be expressed as a closed formula. Okay, we won't prove all this here. These are known from the study of Pell's equation. So taking x and y equal to these Pell numbers, we can then calculate the lowercase x and lowercase y, where the lowercase x is the house number and lowercase y is the total houses in the street. So we have this table. So again, the only solution in this range is this, and the corresponding x is 204. So this is the same solution as we got before. Method 3. From Pell's equation, we know that y squared minus 2x squared is approximately 0, or y squared is approximately 2x squared, or y squared or x squared is approximately 2, or y over x is approximately root 2. Of course, y over x cannot be exactly root 2, but it should be close to root 2. So expressing root 2 as a continuous fraction like this, we obtain on truncating at the first plus sign 1, or 1 upon 1. Truncating at the second plus sign, you get this 1 plus 1 over 2 or 3 over 2. Truncating at the third plus sign, you get this. That is 1 plus 1 over 2 plus 1 over 2 or 7 over 5. Truncating at the fourth plus sign over here, we get this or 17 over 12. The terms in the odd numbered positions are solutions to y squared minus 2x squared equals to negative 1, while the terms in the even numbered positions are solutions to the Pell equation y squared minus 2x squared equals to 1. And from this, we'll get the solution to our problem. If we go further to the next fraction, if you found this interesting and you have people who are interested in preparing for a maths exam, you can contact me at this WhatsApp number 012-656-9840. Thank you and goodbye.